logarithmic function. A logarithmic function, or log, is the inverse of an exponential function. An exponential function has the base b, so the logarithmic function must also have the same base b. Now, why do we call it the inverse? So if we take log base b of b raised x, the log b and b part simply would get cancelled, even though cancelling is not the right term to use, but it's an easier way to remember this. So log b and b would just go away, giving us simply x. So base b logarithm will undo what an exponential base b function did. So log b is undoing b raised x, giving us simply x. So if you look at the curve, the inverse function typically is the reflection about the origin. So this is the exponential function, and that is the diagonal line passing through the origin. So you can see that this curve is the flipped version of that curve. So the logarithmic function is the inverse. The domain of logarithmic function is from 0 all the way up to infinity. So keep in mind, we cannot include 0 because this is going to go along 0, along the y-axis, but it would never cross the y-axis. So it will never have a fixed value at 0. It's pretty much undefined. And the range here for a logarithm is all positive numbers. So we have 0 up to infinity. But you can see zero is a possible value because y becomes 0 there when x is 1. So 0 is feasible, and negative infinity is also feasible because the curve is going down. Some textbooks would like to limit the range of the logarithm from 0 to infinity, starting here and beyond, even though that is fine. The precise range is minus infinity up to infinity. The graph of a logarithmic function, base b, would pass through the point x is equal to 1, and the corresponding value of y is 0, so the point is 1, 0. The graph has a vertical asymptote at x is equal to 0. If you recall, the exponential function has a horizontal asymptote. The logarithmic function would have a vertical asymptote because they are inverses of each other. The x-intercept here is x is equal to 1. If you recall, exponential function has y-intercept equals 1. And recall, exponential function has a horizontal asymptote. And you cannot take log of a negative number. Means it is undefined. it doesn't exist. Good. So we want to write each equation in its equivalent exponential form. So we look at the base first, which is 7. So we raise it to the power of 7 on both sides. So just like log b and b gets cancelled there, or they kind of cancel, these two would go away, and leaving us with simply 7 raised 3 equals x. And that's right there, 7 raised 3 is an exponential form. So here we have a base of b. So we want to raise it to the power of b on both sides. So those two terms sort of disappear. We'd end up having 25 to be equal to b squared, and that is the exponential part. Likewise, we observe a base of 4, so we raise it to the power of 4 on both sides. So those sort of go away. We'd simply have 26 equals 4 raised y. Now we want to write each equation in its equivalent logarithmic form. So we observe the base, and log base 2 raised 5 equals log base 2 x. These two would sort of go away, leaving us with 5 equals log base 2 x. Similarly, we observe the base there, which is b, so we have to take log base b on both sides. Those two go away. We simply have x is equal to log base b of 27. So here, the base is e. So we have log base e of e raised y equals log base e of 33. Those two would sort of go away, and y is equal to log base e of 33. So example 3 has logarithmic equations. So if we want to evaluate it, we typically take exponentials, or if we solve logarithmic equations. But in this case, we simply have numbers here. So log base 3 of 9, I could write 9 as 3 squared equals y. And we know that the log base 3 and the exponential base 3 would go away, leaving us with y equals 2. So here we have log base 36 of 6 equals y, and I want to write that 6 in terms of the base, which is 36, so that I could use a trick like I did in the previous part to get the solution. So I could write 6 as 36 raised 1 over 2. The reason being the square root of 36 is 6. So these two would disappear, and we'll have y equals 1/2. In the next case, we have log base 5, 1 over 125. 125 is simply 5 cubed. You may ask me why am I writing this in terms of 5, because the base is 5. and if I write it in terms of the base 5, then I could use the trick that I used in the previous two parts. So log base 5, 5 raised to negative 3 would equal y. Those two would sort of go away, would end up having y equals negative 3. So here are some properties of log. Before we get into logarithms, if we have a base 10, we simply call it as log of x. But if we have a base of e, we call it ln of x. So we know that e is the natural base, hence ln is called the natural log. So there isn't much of a difference. It's a matter of convenience, and pretty much in mathematics we use natural logs more often than we would use base 10 log. So the properties of log, as you can see, they are pretty much the same across the spectrum. In other words, whether you have a different base b, or you have base 10 or natural log, the properties remain the same, which are log base b of 1 would be 0, log base b of b would be 1, log base b of b raised y is y, and b raised log base b of x is simply x. So remember the trick, those two sort of go away, giving us 1. Those two go away, giving us 1 times y, which is y. Those two go away, giving us 1 times x. You end up getting x. Keep in mind, this is simply an easier way to remember the properties. It is not a formal way of interpretation of logarithms. So those two would simply go away. We have 1. Log of 1 for any base is 0. So that would become 0. Those two would sort of go away, and we'd simply have 8. Those two would go away. We have 17, because the bases match and there is a log in the middle. And I could write this as 10 log base 10 of e, because when we refer to log, we are referring to base 10. So those two would go away. And the answer would simply be 6. Ln of e is base e log, so those two sort of go away, and we'd end up getting 1. The natural log is base e raised 8.2. Those two go away, we have 8.2. In general, if we have ln, it'll just get cancelled of that sort. Again, I'm using the phrase that sort because it's not a formal way of interpreting natural logarithms, but it is easier to look at it this way. ln kind of crosses out e, and we have 1 raised 1 times 8.2, which would give us 8.2. Here, we could write log base 6, 6 raised 1/2. Those two sort of go away, you'd end up getting 1/2. So we know the domain of the domain is from 0 all the way up to infinity. This is for a logarithmic function. So what second case, we start with the domain of the standard logarithmic function, which is 0 to infinity. I could write that as log negative x minus 5. But this could easily get confusing because there is a negative in there and we can't have negative numbers inside a logarithm. But the reason why I'm writing it this way is perhaps it would become more obvious in terms of deriving the domain if we wrote it or rewrote it in this form. So what do I mean by that? So there is a negative, so the domain for f of x has to be multiplied by negative, so we have 0 to negative infinity. Then we have subtracted by 5, which means shifting to the right, but there is a negative in front, so we actually have negative 5, negative infinity. But negative infinity has to be the lower number always, so it becomes negative infinity, negative 5. If you don't want to take this approach, you could simply ask the question, well, what is the largest positive number that we can plug in for that should be a 5. Largest positive number that we can plug in for x, it has to be 5, because 5 minus 5 would be 0, and that is the smallest value in the domain of log. And I can plug in any number less than 5 to keep this part positive. If I picked a number greater than 5, for instance 6 for x, then I'd get log of 5 minus 6, which is negative 1. And we can't take the log of a negative number. So the domain here is negative infinity. So you look at this function in part C. First thing we have to do is to try and rewrite x squared minus x minus 2. How can we rewrite this? I could rewrite this as x minus 2 times x plus 1. So we would have ln of x minus 2 times x plus 1. If I plug in 2, then we'd end up having ln of 0, which is undefined. If I plug in negative 1, we have ln of 0 becomes undefined. So clearly we want x minus 2 to be greater than 0, and we want x plus 1 to be greater than 0, because we can only take logarithms of positive numbers. So this would mean x is greater than 2 and x is greater than negative 1. So if we combine the two conditions, we would simply have x to be greater than 2. So the domain is 2 all the way up to infinity. Easier way to look at it would be 0, negative 1, 2, so greater than negative 1, and greater than 2, so that is the common interval, so the domain has to be 2 to infinity. In the second problem, or in part D, we want x plus 1 to be greater than 0. We want x minus 5 in the denominator to be greater than 0. So this would mean x is greater than negative 1, and x has to be greater than positive 5. So if we plug in any number less than 5, we'd end up having a negative in the log. We can't plug in x equal to 5 because if x is equal to 5, we would end up having log of x plus 1, which is 5 plus 1, divided by 5 minus 5, which is log of 6 over 0, and that is divide by 0, and we cannot do that. So this would imply the domain is 5 to infinity. So we have negative 1, 0, and 5. The first condition is x has to be greater than negative 1. The second condition is x has to be greater than 5. So the common area or the common interval is that. So the domain is 5 all the way up to infinity. So we want to graph the function log base 3 of x minus x. We know what log base 3 of x would look like. So, it's quite arbitrary. So that's just what a log function would look like. If you want to be precise, we'll evaluate it at 2 more points. Log 3 of 3 is 1. So I would have 1 there. So perhaps I'll just draw it that way. And it's just an approximate curve. So that is log base 3 of x. Now we have x minus 6, which would imply that we are shifting to the right by 6 units. So I'm at 1. If I shift, I would end up at 7. Here we are at 1. If I shift, 3 plus 7 would be 10. So have that. And we'd have a curve of that sort. And that would be log base 3 of x minus 6. So here in part B, we have 3 plus base log of x, or base 10 of x. The reason being, log x simply implies log base 10 of x. And which would mean log 10 of 10 would be 1, because the bases match up. These two, the log 10 and 10 sort of go away, and you end up getting 1. So we know that the function becomes 1 at 10. And x is equal to 1, log base 10 of 1 is 0, because any base log of 1 is always 0. So it's going to go like that and down. So that is a typical log base 10 x curve. And I am adding 3 to it, so we're going to shift up. So from here, add 3, we'd come up to 3. And from here, at 10, we add 3, we'd come up here to 4. And it is going to look like that. And that is 3 plus log x. So here are some examples. We want to evaluate log base 3 of 27. We could do this without using a calculator. We are going to try and write 27 in base 3, which is 3 raised to the power of 3. because 3 times 3 times 3 is 27. These two sort of go away, so the answer would simply be 3. So e raised square root of 5 is 2.7182 raised square root of 5. Unfortunately, we cannot evaluate this without a calculator. So you can use a calculator and evaluate it. And the answer is 9.36. Here, we want to write each equation in its equivalent form in the sense that we want to rewrite it in its equivalent exponential form. So if I take or exponentiate on both sides, we can write it in the exponential form. Log and log base 10 are one and the same, so I'm going to raise it to the power of 10 on both sides. And those two would sort of go away, which should imply 10 raised 5 equals x minus 1. X would equal 1 plus 10 raised 5, which is x is equal to 100,001. So the exponential form holds true here, but since we are starting with an exponential form, the equivalent form in this equation would be logarithmic. So we want to take log on both sides, and the base here is 7. So log base 7 of 7 raised y equals 200, and those two sort of go away, and we'd have y equals 200. Sorry, that's bad math. If we take log on one side, we have to take log on the other side. So log base 7 of 200, which would imply y equals log base 7 of 200. We want to find the domain here. We require for any log the value for which we are taking the log has to be bigger than 0. So x plus 4 has to be greater than 0, which would imply x has to be greater than negative 4. So the domain is from negative 4 all the way up to infinity. So here we have x minus 2, and we'd like to know the domain. We know the domain of log base 5 of x is 0 to infinity. And x minus 2 would simply be shifting to the right. In other words, we have to start at 2, because when I plug in 2 minus 2, I get 0. So could I plug in two? I cannot, but I can have close to 2, so 2 all the way up to infinity. I could put any number I want here. And this is going to just work. Now, could I plug in a number between, say, negative 2 and 2? So I can, because what we have here is x minus 2 squared. So I could plug in any number in x minus 2 squared. of course, except 2, and we will get a positive number. So what we're saying is I can plug in any real number over here, except 2. So what is the domain? The domain is negative infinity up to 2, union 2 to infinity, because we can't plug in 0 because, plug in 2, because when we plug in 2, 2 minus 2 would become 0. But I can plug in any other real number just because of the fact we have x minus 2 raised 2. So no matter what real number I plug in for x minus 2 raised 2, this would always become positive, so I could plug in all real numbers except x is equal to